Well, hello, everybody. Welcome here to homework number 2. If you're coming to this homework first, if this is the first homework you're coming to, since you realized at some point homework 1 is not actually, well, I should say I don't have access to your homework number 1. So that's why we're not starting with homework number 1. But I did make a homework 1 video as an introduction to what this series is about. If you want to go check it out, it'll be on my channel all in a playlist for Math 1200. But if you're here to actually get some work done, you came to the right place. Homework number 2, folks. Week number 2. Due January at some point. This date is not live, but we're gonna go through the problems and we're gonna explain concepts and then an attack as quickly and as efficiently as possible once we really get a basis. And if I feel the basis we've already covered or you should already know and there's a gap missing, let me know in the comments and we'll figure out a way to fill in those gaps for you. But without further ado, let's get into the supplementary problems. Homework number 2. Yeah, homework number 2 and problem number 2. Evaluate each expression based on the following table. So the skill that they're testing here right off the bat is using this table and reading information off of it. And this is actually something that I talk about quite a bit with my in-person students, is the fact that math in general and calculus as a subset of math in general is like learning a language. So everything that we do is about translating what we read on the paper into a language that we can understand in our brain, a notation language that we and the teacher are communicating using, and therefore communicating our process and our logic step by step in a way that's, again, understandable and reinterpretable by anyone who speaks any other verbal language. It's a cool kind of universal language that we get to communicate with, and hopefully that the way that we communicate, even though it's kind of a one-way communication at the moment, is a way that you can understand with your current subset of information and logic, and that we can little by little expand the information set that you can comprehend and use so that the language of math becomes a lot more easy or facile to you. Okay, evaluate each expression based on the following table. So how I read this is f of 0. Okay, so the of 0 part, or just the 0 part, that's denoting or indicating the x value. The f of portion, if we were looking on a graph, the f of x would be the y. So y equals f of x. And then the horizontal axis is the x. So in other words, the x value is our input and our f of x, or the f, is the output, right? So in a function, like in a business operation, you have inputs and outputs. You have the efforts and the labor and the capital that you put in to a business, and you have the end result, the product, the profit, as the output, the growth of the business. Whatever your input output equation or function is, any mathematical function maps one to the other. And typically we consider the inputs as independent variables and the outputs are dependent on the inputs and a function that relates them. But regardless, this is just testing our ability to use this particular table. So as you can see, there's a lot of foundational stuff that goes into even just reading what we have here. So in being able to read f of 0, basically what we have to do is we have to find x equals 0, and then we find the f of 0 that maps to 0. So in just reading that table, f of 0 is 2, right? So if you didn't know what all of those concepts that went into it, you might just see this 0 here, and think that's what f of 0 is. And then you might say 3 or whatever. But the key thing here is that the x value is what's in parentheses, and what we're trying to get out of the function here is the y value, which is f of whatever, but f of 0 in this case. I was going to mention something else, but let's keep going. Okay. B, f of -2. So we find x equals -2, and then we go down and have, so f of -2 is equal to 1.5. Boom. F of -1 plus f of 2. So we're going to take the result of each of these and then add the results together. Oh yeah, I remember what I was going to say. So mathematically, a function is, so you have all these different x values. So -3, -2, -1, 0, 1, 2, 3. So those are all our x values. In a function, a true function, every x value can only have one output. So you could not have two different f of -3s. You can only have one f of -3. Now, if you have some graph, if you have a graph that's a circle, for example, a circle is not a true function, and you can test it with what they call the vertical line test, if you remember that from high school or whenever you took algebra, whatever, algebra 1 or algebra 2, I don't even know at this point. But the point is that if you do the vertical line test, you see that an individual, right, again, the concept is that an individual x value, so say this is x equals 1 over here, there's two different y values, right? So y values are along the vertical axis, the tick marks there. So let's call it 3, right? So let's say this was 2 and that's 1. So let's say this y value was 3 and then this one was -3. So you have, for x equals 1, you have y equals both 3 and -3. So this is not a single function, this circle. It's actually it's two different functions put together. And we can call that a piecewise function, but that's neither here nor there for the time being. I just wanted to insert that point about functions being a situation where each x value can only have one single y value that corresponds with it, that goes with it. Okay, so for f of -1, we have f of -1 is 5. So this equals 5 plus f of 2 is -0.25 plus -0.25. So I have the plus sign in between corresponding with that. And I just put this in parentheses to let the negative kind of be enclosed and differentiated, because you can't really have plus minus like that. It's really plus negative. And that's, if you were to put in your calculator, you could do minus 0.25, and that mathematically is equivalent, but notationally is a little bit distinct. So theoretically, you could also put that in parentheses and that would look nice and clean, but you got options. At the end of the day, again, it's a language. It's about communicating your understanding to the person reading it. So this works. I like that for now at least. But if I had 5 plus positive 0.25, I probably wouldn't put parentheses. But anyways, 5 plus -0.25, 4.75. D. As much as possible, I encourage you to not use a calculator whenever you can. It trains your brain in a really fun and / funky way. And it's something that I like to exercise. So sometimes you'll see me even excessively trying to just struggle through calculations that I could just plug into a calculator, but it's good for my brain. It's good for your brain. I encourage you to give it a shot. D, f of 3 times f of -3. Okay, so we're going to take the results of each one and then multiply the results together. Again, just recommunicating that into language that hopefully makes sense to you. So f of 3 is 0. I almost wrote plus, but we're going to multiply that times f of -3, which is 2. So 0 times 2. 0 times anything is 0. Great. Part E. F of -1 over f of 0. So f of -1 is 5 and f of 0 is 2. And again, I'm putting it in parentheses, but in this case and in many cases you really don't need to. But again, we'll keep clarifying. I'll let you know as we go along what's necessary and what's choice, what's convention, yada yada. So 5 divided by 2, 2.5. You could leave it as 5 over 2, but they seem to be using decimals in this problem, so we'll stick with that convention. What do you know? I did what I said I was going to do. Okay, this, we have 5 times f of 2. F of 2. So x equals 2. F of 2 is negative 0.25. So this is equal to 5 times negative 0.25, which is negative 1.25. Yay. We did problem number 2, which was our first problem. And I wrote number 2 again. All right. So now we're on problem number 3. Oh, wow. Okay, number 3. Make it a little bigger. Okay, so find the domain of the following functions. Ooh, what is a domain? We have a new term to understand now. So the domain is the set of x values, which can be plugged into a function. Just so you have that written there. But basically, we're trying to figure out which x values are allowed to be put into a given function. So conversely, our task is to find out which x values are not allowed to be plugged into the given function. So once we find out which x values cannot be plugged in, all of the other potential x values can be plugged in. So our baseline to start with in these situations is negative infinity to infinity. That would be for a good chunk of functions that are out there. That's going to be our domain. It's going to be all the possible numbers. So let's start here with a f of x is equal to x plus 1 over x to the 4th. So let's pretend that it was just f of x equals x. That would be an example where you could have negative infinity to infinity. Any x value could be plugged into the function. Again, any value of x could be substituted for x, and we wouldn't have any mathematical issues. However, in this situation, we have x plus 1 over x to the 4th. I kind of wrote that weird, didn't I? 1 over, or did I move it? I don't know what happened. 1 over x to the 4th. So whenever we have a fraction, okay, so even if it were just 1 over x, we are asking ourselves the question, well, again, in general, what would cause a problem? What would cause a problem in this situation? What can we not divide by? The answer is 0. You cannot divide anything by 0. 1 divided by 0 is undefined. Big no-no. So in any situation, if you take a look at f, for example, we have two different things on the denominator. But fundamentally, if the denominator itself equals 0, then that would be considered a problem. So in this case, since we have x to the 4th, it's x equals 0 is a problem, right? Whereas in C, for example, we have, if we were to plug in x equals 5, 5 minus 5 equals 0, so that's a problem. X equals 5 is a problem. But in this case, we just have x equals 0 as a problem. So the domain is going to be listed as follows. And so we're going to use interval notation for this. So we have, again, our baseline is negative infinity to infinity. So we have negative infinity, in this case, up until 0, but not including 0. So this I call soft parenthesis, means it's exclusive, versus a, quote, hard bracket, which is inclusive. That's just the way that I refer to it as, just to remember the shapes. Soft parenthesis, hard bracket. And soft parenthesis is exclusive, and hard bracket is inclusive. And anytime we have infinity involved, it's always going to be a soft parenthesis, because infinity is not a number, a hard number, which can be included. And then we have this symbol that looks like a U, but it's called union, which joins two different intervals together. So this domain is going to be negative infinity to 0, union 0 to infinity. Again, all soft parentheses there. So it's basically all values except x equals 0. And it's implied that the domain, is referencing the set of x values. And with all that context at play, we should be able to move through B through F fairly quickly. So g of x is equal to the square root of x minus 4. So the square root of 1, for example, what's the square root of 1? Well, are we talking about the positive square root or the negative square root? What I'm getting at, my point is that the square root of 1 could be 1 or negative 1, meaning that negative 1 times negative 1 is positive 1. So negative 1 squared is equal to positive 1. Positive 1 squared is also positive 1. Therefore, the square root of 1, we could be talking about the plus or minus, plus positive or negative square root. With that being said, we are not going to be able to, unless we're talking about imaginary numbers, we're not going to be able to take the square root of a negative number. So that's not equal to, so the negative square root of 1 is not equal to the square root of negative 1. Very important difference there. So what that means for our domain is that the minimum, the lowest number that can be inside the square root is 0. So the square root of 0 is 0, right? So 0 squared is equal to 0 times 0, which is 0. So we can have the square root of 0. It's not very eventful, but it is valid at the very least. So this means that x has to be greater than or equal to 4. And the way that we would write that domain in interval notation is going to be, again, hard bracket this time because it includes 4. It can be equal to 4, 4 comma infinity. That's our domain. And typically, I like to box my answers, and your teachers will like you to box your answers. So you can box this domain, but to be honest, in a problem like this, when you're communicating it very clearly like this, it's pretty obvious what your answer is. So if you get in trouble for that, you can blame me. I'm okay with that. But I might leave my answer like this. If I was feeling like I wasn't sure, I would box it. So if you're a little bit more risk averse, box it. If you like to live a little bit on the edge, see what you can get away with for now, at least, just test it, test the theory. I'll leave that up to you. Anyways, part C here, k of x is equal to 7 divided by x minus 5. And we talked about this a little bit before. Our domain is going to be everything except for x equals 5. Negative infinity, comma 5, soft bracket, or soft parentheses, excuse me. So, and if I wanted to notate that there, I would say, just like how I said x is greater than or equal to 4, here I would say x is not equal to 5. Just to kind of summarize. And oftentimes, even in problem statements, as you just go through this course, you'll see something like this next to a function to clarify the domain, but explicitly written, this is what the domain is in interval notation. To be honest, I'm going a little back and forth on whether I would box this if I were truly a student. I mean, I'm always a student. I'm a student of life, right? Am I right? Am I right? But if I were a student in your class, I might actually ask the teacher. That's probably what I would do, to be honest. Do you want us to box every single answer? Do you want us to box it even when it's obvious beyond the shadow of a doubt what the answer we're presenting is? I would ask that question. I was that guy. I am that guy. I don't know what to tell you. That's just how it goes. And that's how I did well in high school. That's about it. And part D, h of x is equal to x squared plus 12. Domain. Again, we ask ourselves the question, what can x not be? And sometimes the answer is nothing. X can be anything. And in this case, that is the case. Negative infinity to infinity is the domain. Okay. J of x is equal to the square root of 4 plus x squared. So still, the portion of the graph underneath the square root cannot be less than 0. However, since we have this x squared portion there, remember, anything squared is going to be positive already as it is. So by virtue of that, the minimum this thing under the square root can be is actually not even 0, but the minimum is 4, because the minimum x squared can be is 0. Not by any rule, but just by the way that it goes, because the anything negative is going to turn positive, and 0 squared is 0. So 0 plus 4 is 4. So the minimum that this thing can be, the minimum thing that what's under the square root is going to be is 4. The minimum it could theoretically be, or it's allowed to be, is 0. But all of that boils down to is that x can actually be anything. The domain is negative infinity to infinity. Regardless of what x is, we're good. We're good underneath the square root. We're not breaking any rules. We're not breaking any laws. M of x is x squared cool. All right, so on the top, x can be anything, even if x is equal to 0 on the top. 0 divided by something is fine. 0 divided by 5, for example. In this case, what it would actually be is 0 divided by 3. If we plugged in 0, 0 divided by 3 is 0. 0 divided by anything is 0. Something divided by 0 is undefined. So that's where we have to get a little more granular here. So x is not allowed to equal 1 or 3. So the domain, negative infinity to 1, union 1 to 3, union 3 to infinity. And that's it. That's our domain. All right, so in this case, now we have 3 different intervals that we consider here. Okay, on we go. Okay, question number 4. When I switched over the pages here, I will tell you that I was like, I could not believe all the problems that were there. Just all the words, not even, we don't know how long or how hard the questions are going to be. But there's a lot of text on this page. So let's do it, folks. They're going to ask us to graph the following functions. So before we go ahead and do that, I'm just going to draw some axes. Probably end up using the same set of axes, and we'll just erase the graph here. Okay, axes, and we're going to label the axes x and y. Y equals negative 2x plus 1. So, business calculus students, do we remember what the form of the equation of a line is? Or at least one of them. We have this one here is called slope intercept. And the format is y equals, say it with me, mx plus b. And that corresponds with the two what are called parameters. M and b here are parameters. M is the slope and b is the y-intercept. So with that said, b here being 1, this y equals 1 is, again, the y-intercept is where the graph, or in this case, the line, crosses the y-axis. So when x is equal to 0, y is equal to b, right? So if we were to plug in x equals 0, 0 times anything, but 0 times m would be 0, plus b, 0 plus b would be b, b would be equal to y. So that's, again, just a little refresher there. And so the slope being negative 2, right? If m is the number right in front of x here, the slope being negative 2, and let's remind ourselves what a slope is. It's the change in y over a change in x, especially in the context of a line. This ratio, this change in y divided by a given change in x, is constant. That's why there's no well, it's just a constant. It's a number. It's a coefficient of x here. So every time x increases by 1, okay, every time x increases by 1, our change in y is equivalent to our slope. In this case, that's negative 2. So every time x goes up or over to the right by 1, y goes down, right? Negative, down by negative 2. So if at x equals 1, y is going to be equal to negative 1. So that's all the information we need ultimately to be able to draw a line. So we can do that. We can draw a line that intersects between those 2 points there. So really all we need functionally in terms of drawing a graph is 2 points, because we can connect those 2 points by a straight line, extend that line, and that becomes the graph. It's not so simple when we have curves, so we may need more points to get the overall shape of it. But for lines, pretty basic. And of course, we have a line drawing tool that just connects the dots, literally. And that's part A. Okay, now for part B, we have a slightly different presentation of what the equation of the line is. So we have 4y minus 3x equals 12. And this is called standard form. So our first task to make it easy to graph is going to be to switch it into slope intercept form. In other words, to solve for y equals, and to get our m and our b accordingly. So we have 4y plus 3x equals 12. 4y minus 3x equals 12. So again, we're going to solve for y basically. So 4y is equal to 3x plus 12. Y is equal to this right side divided by 4. So 3 over 4x plus 12 divided by 4 is 3. So this is our m, and this is our b. So we have 1, 2, 3. Okay. And our slope is going to be 3 divided by 4. So again, our slope, our m, is equal to a change in y divided by change in x. So for a given increase in x of 4, we're going to have an increase in y of 3. So 1, 2, let's go the other way actually. 1, 2, 3, 4. So this is -4. So for a decrease in x of 4, we're going to have a decrease in y of 3. All right, so 3 becomes 0 in y as we go 4 to the left. And now let's just get our line tool, and we're going to connect these 2 points, extend them, extend the the arrows, extend the arrows onwards and backwards. And that is the graph. Number 5, find the equation of the line through the point 2, -3 with slope 1/2. So same deal. We're writing the equation of, well, I guess in this case, we're just creating the equation. But the presentation of this information is going to bring me to a different way of expressing the line, which is a point slope equation. So we're given the point 2, -3, right? That's one piece of information. And we're also given m equals 1/2. So instead of doing y equals mx plus b, and we can always rearrange this into that format if that's what we're comfortable with. But point slope is a good one to know as well. And just to close the loop again on standard form, it's a y plus bx equals c. That's standard form. And then point slope is y minus, let's call it y0, equals m times x minus x0, where our point is some x0 comma y0, and our m is our slope. Same deal, same m. And again, you can always rearrange this, right? So the way that you rearrange it is you distribute the m. So you would have y is equal, and then move the y0 to the other side. So you have y equals mx minus m times x0 plus y0 is equal to mx plus b. So this m times x0, or I guess it'd be y minus m times, or y0 minus m times x0 is equal to b. Yeah, that's how that works. Ultimately, the point is that you can write an equation like this, and that is sufficient to describe the equation of the line. So we can write this as y minus -3 equals 1/2 times x minus 2. So that's sufficient. If you want to leave it there, you can. That is okay. At least if I were your teacher. And in this situation, I am your teacher. Just kidding. Kind of. I am your teacher, but I'm not grading you. So feel free to do what you need to do to appease and please your teacher, because that's part of the game. Okay. And then we can distribute this m, right? So this ends up being 1/2 x minus 1/2 times negative, or 1/2 times 2. So it's 1 minus 1. And then we move this to the other side. So that's y plus 3 over here. And then when we move it to the other side, it's minus 3. So y is equal to 1/2 x minus 4. That's the same thing as this. And if you wanted to correct the negative situation there, make it into a positive situation. Y plus 3 is equal to 1/2 times x minus 2. So this is the same as this. That's how it goes. Number 6, calculate the average rate of change of the given function over the interval 0, 3, inclusive, right? Those are those hard brackets. So we have some new terminology here. Calculate the average rate of change. Okay, So average rate of change is if you take an overall rate of change. So we could, or an overall change, shall we say. So if we were to graph this situation here and ignore the endpoints for a moment, if we had our x equals 0, p of x is equal to -10. So let's call this -10. Our p of 0 is -10, and our p of 3 is +10. So 1, 2, 3. So our total change, meaning our p of 3 minus p of 0, is equal to 10 minus -10, which is 10 plus 10. So it's a change of 20. In other words, our change in p is equal to, our change in p, let's say from x equals 0 to x equals 3. This is some new notation, but this vertical line it allows us to indicate particular x values, is equal to 20. So our average rate of change, right? Like if you were driving a car, you could have your average speed. That would be an average rate of change. Your average speed would be how many total miles you went divided by the total amount of time that it took you to travel a certain number of miles. So our average rate of change here is basically delta p over delta x, again from x equals 0 to 3. So in that case, we already know our delta p is 20, and then our delta x, our change in x, is 3 minus 0, which is 3. So it's 20 over 3. That's our answer there. And that I for certainly would box, honestly, personally. That would be our average rate of change. So basically, it, regardless of the fluctuations that take place in between, right? So our p of 1 is 30, but for the purposes of calculating the average rate of change, that's inconsequential. So you have a data point up here, and then our p of 2 is 25. Right, so we don't know the exact shape of this thing, something like that. I don't know, but it could be like something like that, right? But now we're just talking about the endpoints of this interval. So p of 3 minus p of 0 divided by 3 minus 0. So formally, delta p over delta x in this case is equal to p of 3, again, whatever, from 0 to 3 in particular. P of 3 minus p of 0 over 3 minus 0. And more generally, change in y. Oh, look at this. What is this? Change in y over change in x. Is that similar to slope, as you may say? Average rate of change is the same as your average slope, right? And you could see we drew a line in between the endpoints, and that line has a certain slope. What do you know? So change in y over change in x, or yeah, and let's call that y of, well, let's make this from x equals a to x equals b is equal to y of b, second endpoint, minus y of a over b minus a. Yay. Number 7. So, following table shows the number of people in the US without health insurance in the years 2012 to 2016. Compute the average rate of change of U of T over the period 2012 to 2016. All right, so our T here is defined as the year since 2012. Therefore, the data for 2012 is listed as T equals 0 because it's 0 years since 2012. Anyways, we get introduced to the fact that it's not just going to be change in y over change in x, or even change in p over change in x, that we can change the variables at play here and still compute an answer. So compute the average rate of change of u of t over the period 2012 to 2016. So we can have delta U of T over delta T, again, from T equals 0 to 4 equals U of 4 minus U of 0 over 4 minus 0. And I put the T of 0 to 4 just to be super specific here. But if you're just solving this, you can just say delta U of T over delta T, and that's plenty all right. So I'm going to move that there. Okay. So that's equal to 28.7. Oh, and the U of T is given in millions. So U of 4 is, did I say 28.7? Yeah. Minus 44.7 all over 4 minus 0 is 4. Okay. So this is going to be negative 16 over 4. Negative 4 million per year. And they say interpret your results. What does that mean? So basically, that's really talking about units and also again reinterpreting it in the context of the question. So that means on average, right? It's average rate of change. On average, 4 million people per year let's say, okay, so this is the number of people without health insurance. On average, 4 million 4 million people per year. Let's say 4 million more. No, let's call it fewer. 4 million fewer people per year did not have health insurance. Between 2012 and 2016. The other way that I was going to interpret it might even make more sense. 4 million, which I was going to say is 4 million more people per year acquired health insurance. And then, between 2012 and 2016. So both are true. Again, it just goes back to the context of how you want to interpret the problem and just being really clear on that. So negative 4 million people per year did not have health insurance. That's the average rate of change. Meaning that 4 million people per year gained health insurance, got health insurance. You get it? You get the point. Thanks, Obama. Number 8. Sketch the graph of a function f whose average rate of change over the interval 0 to 2 is negative, but whose average rate of change over the interval 0 to 4 is positive. Okay, so y equals f of x. This is x. So we have 1, 2, 3, 4. 2 and 4. So let's start with the overall interval. And we can keep this really simple. So we can start at the origin. And basically at x equals 4, our let's call this f of 4. So basically f of 4 minus f of 0, right? So the average rate of change, f of 4 minus f of 4 of 0. f of 0 over 4 minus 0 is greater than 0, right? It's positive. That's what they say. So what that means, since 4 minus 0 is going to be positive regardless, f of 4 minus f of 0 also has to be positive in order for the fraction to be positive. So all that means is that f of 4 has to be greater than f of 0. So since we're starting at f of 0 equals 0, f of 4 just has to be positive. And if we, again, draw a straight line in between, we have a line which has an m that is positive, greater than 0. And that's how that works. Okay, but now if we're looking at the average rate of change from 0 to 2, that's negative. Again, 2 minus 0 is going to be positive. So that means f of 2 has to be, since we chose f of 0 as 0, f of 2 has to be negative. So now we can just connect the dots, make it into a fancy little curve. And we could even draw it as a parabola, something like that. And that's one option. We're just sketching a graph. Believe it or not, that's how it works. I'm having fun saying that. I hope you get that I'm just having a grand old time. That works. If you get something that looks different, that's fine. But I think we covered the key points that f of 2 has to be f of 2 has to be less than f of 0. And f of 4 has to be greater than f of 0. That's it. Number 9. What's you gonna do? 6 point. This is a 6-pointer, folks. Real big, real big. According to the U.S. Census Bureau, the population of Denver, you and me, we're in Denver, was 467,610 in 1980, 492,686 in 1990, 554,636 in 2000, and 600,158 in 2010. Between 1980 and 2010, by how many people did the population of Denver grow? So this is not asking anything about average rate of change. Don't just get into no habit here. You got to read the question, listen to what they're saying, and just say, by how many people did the population of Denver grow? Okay. We're going to get to the average in the next one. Okay, so this is okay, so I'm going to set some context here. Oh, they already give us an equation. Basically, but let's use their thing here. So P of basically 2010 minus P of 1980. That's what we're looking at here. Alternatively, you can call it delta P, change in population, is 600,158 minus 467,610. Okay, so this is going to be 32,548. 132,548. Yep. Okay. And that I would box that. B. In an average year between 1980 and 2010, by how many people did the population of Denver grow? Delta P over delta T is equal to 132,548 divided by, let's call it 2010 minus 1980, because that's what it is. That's how it works. 132,548 divided by 30. Okay, so we can take away one. We can add it, basically move the decimal point, and then divide by 3. So 132,000. That's going to be 44,000. Yeah, 44,000. Or no, I mean, 132 divided by 3 is 44. Yeah. 44 and then 548. So it's not going to be exactly divisible, but let's see. 167. It's going to be 180. Okay. Yeah, 50. 54 is divisible by 318. So 1/8. Right there. Yeah. And then 2.67. 44,182.67 per year. Let's call it people. People per year. That's I made a mistake. I was like, that's kind of a lot. It's not true, folks. I messed up. I didn't move the decimal point. 4,418.2.267. So let's call it 4,108, 4,418.27. Let's check my math here. Yep, that's our answer. 4,418.27. Wonderful growth, Denver. Good job. Great job. All right, that's 4,418.27 people per year. Yay. Woo-hoo. By how many people? That many people per year. Okay. C. Let P of T represent the population of Denver at time T, where T is measured in years from January 1st, 1980. What is the average rate of change of P on the interval T? Well, we already did that, didn't we? Come on. I'm just literally going to copy paste it here. Unless they're asking something different. Let P of T, what is the average rate of change in the interval? Yeah. Come on now. I think they're just changing up the language on you, on us, because we're in this together, guys. Let's be honest. We're totally in this together. Okay, if we we're moving on. They were just switching it up, throwing us for a curveball here. Wild, just getting us used to different notation, I suppose. If we assume that the population of Denver is growing at approximately 7% per decade, we can model the population function with the formula P of T. So sometimes I'll do this, often I'll do this really, is notate important information from a problem when I'm starting my solution. 1.07 times T over 10. Okay. And that gets you again thinking in terms of that language model of, well, thinking of math as a language, and you're taking notes like you might on a history text or something like that. In this formula, T is still measured in years from January 1st, 1980. Using this formula, compute the average rates of change of the population on the intervals 10 to 15, 11 to 15, 12 to 15, 13 to 15, 14 to 15. Okay. Fine. Okay, we'll get to work, I suppose. That's some work right there. Okay. I almost want to like do these sub problems here. Okay. P of 15 minus P of 10 divided by 15 minus 10. So that's the process here. And then 2 is going to be P of 15 minus P of 11 over 15 minus 11. Yeah, this is like for 6 points, they're really pushing us. They're really pushing us, honestly. Aggressive. 15 minus 12. All right, we get the point. Everything's set up. Now it's just a question of plugging everything in. So P of 15 is just going to be, we can calculate P of 15 separately since we're going to use it a lot. P of 15 is equal to 467,610 times 1.07 times to the power of 15 over 10. So 15 over 10 is 1.5. So it's going to be 1.07 to the power of 1.5 times 467,610. And I know, guys, I said I would push myself and I would encourage you to do as much as you can in your head, but I'm not going to do this one in my head. So after setting that up, that's what we get. So that's how many people are, at least by this model, supposed to be living in Denver in the year, what is it, 1995? Yeah, it's halfway in between. Okay, now we'll just go through calculating. I'm just going to calculate all of the other ones. So 14, 13, 12, 11, and 10. And we'll be right back very soon. I mean, it'll be instantaneous for you, but go ahead, do this by yourself. Go ahead. Go. Do it. I'll see you in a second. Okay, so this is what we got for each of those values. So for 15, we got 517, 558.5. And even though I write this 1.1068 in the calculator, I'm using the expanded version to get this number, just in case, FYI, you get slightly different rounding stuff. So just take a look at these. Basically 514,000, 510,000, 501,000. Okay, so there's a discrepancy here. I got to check out 12 versus 11 here. That's better. 507,000, 503,000, and 500,000. So the reason I knew it was a discrepancy is because it's going in one direction. It's going, as we get closer back to 1980, should be getting closer to 467,610. And so that 501,000 didn't make any sense. So that's a good note for you. So when you're going back and checking your work, you can notice, I mean, if you can notice those little patterns, obviously if you do it the first time, that's the best. But when you're going back to check your work, if you notice some kind of discrepancy there, so it's like just looking down, oh, that doesn't look quite right. And then figure that out. So anyways, those are all the P values, the population numbers in each of the necessary years. So then now I'm just going to copy paste it, plug it into the formula, and then we'll come back and check our answers. Well, here we have it. Using this formula, compute average rate of change of the population on the intervals 10, 15, 11, 15, 12, 15, 13, 15, and 14 to 15. And we have all of those right here. So we have 3, 4, 4, 3. I'm just rounding to the nearest whole number. 3, 4, 4, 3, 3, 4, 5, 5, 3, 4, 6, 6, 3, 4, 7, 8, 3, 4, 9, 0. So the average rate of change is increasing. And again, all of these units are people per year. People per year. Considering your work from Part D, how fast do you think the population of Denver was changing on January 1st, 1995? Okay, how many additional people should the city have expected the following year and why? So 1995, that's 15. This is an interesting question. So we're basically being asked to project out as to the basically the instantaneous, because these are the average rates of change as we go year to year. So it's an 11 to 12 increase per year. So let's take that information and we'll say, so that's effectively what we're looking at is P. If we were to be able to say an average rate of change, what they're trying to get us to start thinking about is P of 15 minus P of 15 over 15 minus 15, which of course is going to be 0 over 0. So that's not what it's going to be mathematically, but what we're thinking about is getting the bottom towards 0. So we're saying, really, how fast is the population changing on that particular day? And let's see how fast. So basically, I'm just going to add another 12 to this. So let's say 3,000. Well, I'm not. Yeah, let's go and keep it in terms of year. I was going to say, are we then thinking about per day? But no, 3,502 people people per year. Great. And what else did they ask? How many additional people should the city have expected the following year? Per year on January 1st, 1995. They should expect another 3,514 people the following year. I think they want us to explain. Let's see exactly what they're asking. Why? Just why? According to the pattern in the model. I'm going to leave it at that. According to the pattern in the model, because it's predictable, apparently. That's it. I'm gonna leave it there. The most recent U.S. Census Bureau estimation for Denver's population is 727,211 in 2019. Do you think the model from Part D will give a reasonable population estimate for Denver in 2021? Testing the model. So we're basically just going to plug in 2019, or I guess it would be 39 into the model. Testing the model gives P of 49, 39. All right. Basically plug it in to the model and we'll see what we get. So we get 608,808, I believe. Yeah, 608,808. So basically the model breaks down somewhere. That's kind of what we get. Do you think they're asking, do you think the model from Part B will give a reasonable population estimate for Denver in 2021? Well, this is what it would be for 2019. Testing the model for 2019 gives 608,808, which is let's call it a significant difference from the 2019 census data. Which, let's say, inspires doubt about the model's long-term efficacy. Something like that, guys. Just showing that you are understanding that the model breaks down for 2019, and therefore that's the basis for why it's probably not going to be a good model to model 2021's population. Let's see what else we got. Core problems. So just so you guys know, in general, the core problems, as it says, are graded for accuracy. So nevertheless, I think always try both the supplementary and core problems to the fullest extent. Like that, especially that last question 9 took a while, even for me, just to go through the mechanics of it. So you're going to be spending some time on these homeworks, and that's a good thing. The time that it takes for you to do it is going to help you improve your skill as you do more problems, meaning that doing more problems and spending the time and just really doing the repetitions is going to make each repetition over time easier and easier. So it's worth it. And you feel better about yourself if you just give it your all each and every time. So even if you're following along with this, I encourage you to try each step of the way and even struggle with it for a while and use this as a way to check your understanding, check your process, and feel like you're being guided along the way in a little bit more of a fashion than you otherwise would just with the typical teaching that you get. Okay, find the equation of a line through the points 1, 2 and -1, 6. So this is now 2 points. So I actually alluded to the fact in our supplementary problems that you can have a line. If you have 2 points, you can draw a line through them, and graphically that gets you what you're looking for. So you can do the same thing algebraically using our point slope. And instead of really being point slope, we're going to use so it's typically y minus y0 equals m times x minus x0. We are going to plug in the x and the y. And ultimately this, I might blow your mind a little bit. I'm just saying, if we rearrange this equation and divide by x minus x0, we have y minus y0 over x minus x0, which is equal to m. And what does that look like if not delta y over delta x is equal to m? Is that crazy or what? Insane. Wild. So that's what we're going to do. We're going to calculate m by this. So we're going to choose this as our x comma y, and then we will do this is x0 comma y0. And you could do it the other way. Actually, let's do it the other way. Excuse me. x0 comma y0, and then this is x comma y. So we have 6 minus 2 over -1 minus 1 is equal to 4 over -2, which is equal to -2, which is equal to m. So that means, and then now we're going to plug back in, or we're going to have it just be y, x and y, and then our x0 comma y0 is still going to be 1 and 2. So we're going to have y minus 2 equals -2 comma or times x minus 1. So again, we can leave it at that. That's good. If you want to give it as y equals mx plus b, then it would be y equals -2x plus 2 plus 2, so it's negative 2x plus 4. Y equals negative 2x plus 4. That's good too. And you can box that answer at the end, or the one, or this one here. Both are valid. All right. Number 11. And just a note here. Actually, I'll save this. I'll save this note for the end, because we're almost done. Median home price in the U.S. in thousands of dollars over the period January 2010 to January 2015 in thousands of dollars can be approximated by the equation P of T equals 4.5 T squared minus 15T plus 180, where T is the time in years since 2010. Compute the average rate of change of P of T over the interval 1 to 5 and interpret your answer. Cool. Okay, so A, average rate of change, delta P over delta T from T equals 0 to, and actually I'm going to show you another way to do this. T equals 5. There's another way that looks, where you have the bottom limit there and the top limit there. So that's what we want to calculate. We need to find P of 0 and P of 5 naturally. So T minus, we can do the delta T on the bottom. So 5 minus 0. P of 0 is going to be fairly straightforward. If you plug in 0 for T there, 0 squared times anything is 0. 0 times 15 is 0. So it's just going to be minus 180, because we're looking at basically P of, I'll write that formula down. So this is going to be P of 5 minus P of 0. So P of 0 is 180 is what I was getting at. P of 5. So P of 5 is going to be 4.5 times 5 squared minus 15 times 5 plus 180. 5 times 5 is 25. 25 times 4.5 is 100. 100 and 5 minus 75 plus 180. So 112.5 plus 105. So 117.5. So that is equal to negative 52.5 over 5. No, it says 62. Yeah, 62. Negative 62.5 over 5. So just a tip for you, in order to divide by 5 in your head, you can multiply the number times 2 and then move the decimal place. So 62.5 times 2 is 125, right? And then we can move the decimal place. So it's 12.5. And of course, the negative stays. Sweet. So negative 12.5. Let's go back to our context here. Again, interpret your answer. Negative 12.5. So let's say thousands per year. And just a quick note on the units overall. So we have our delta P over delta T, or change in P over change in T. The P, again, is in thousands of dollars, and T is in years. So it's literally thousands of dollars divided by years, or thousands of dollars per year. Thousands per year. $1,000 per year. We can also just call it, let's do that. Negative 12,500, maybe not thousands, but whatever, thousands per year. Is it the median, or what did they call it? Median, yeah. The median home price dropped an average of $12,500 per year from January 1st, the 2010 to 2015. Am I correct? Yay. Cool. That's our answer. Median home price dropped an average of $12,500 per year from January 1st, 2010 to January 1st, 2015. Period. Okay. So estimate the instantaneous rate of change of P of t at t equals 1. So and this might actually reference back to one of the supplementary problems. And if I were to go back, I would probably redo that. But as you can see, all of my work is gone. So if you want to go back and edit that part, that would be great. But this is what I would do to estimate instantaneous at t equals 1 is I would do the average rate of change from 0 to 2. So delta P over delta T from T equals 0 to T equals 2. And basically what that does is it puts T equals 1 at the midpoint. So before we really learn how to get the instantaneous rate of change to estimate it, you basically put the T equals 1 at the midpoint and use that as a proxy for the instantaneous rate of change. So basically the idea is that as you decrease that delta T, you get closer and closer to the true instantaneous rate of change. And again, that's what this whole calculus thing is all about, but we don't have to talk about that fully yet. So, but we're going to do this. P of 2 divided by P of 0. So right now our delta T is 2. So we can definitely afford to get that smaller. So, I mean, but right now this is fine. So like, again, you could do 0.5 to 1.5. You could do 0.75 to 1.25, and that would get closer and closer to the real deal. But again, this interval is fine for now. And circling back to the previous problem, and like we can take a look at that at the very least, so I can just guide you on your way. For E, we could call we would do P of 16 minus P of 14 over 16 minus 14, and that would get us an answer. So and then yeah, that would be that answer. And then how many additional people? You could actually do P of 16 minus P of 15, and that should get you an answer for the how many additional people. And then the Y, again, what we talked about earlier is, again, one interpretation that would suffice to show your attempt and your effort. But another explanation of this is using the model. That's ultimately what we're looking at for that one. Is your justification is somehow based on the model. So if you're doing P of 16 minus P of 15, that would it'd be a slightly different explanation, but in that case it would be using the estimate of the model for the population of Denver in 1996 and subtracting it from the amount of people in 1995. Actually, I'm sorry, I take that back. Let's use how many additional people the city expects in the following year. I take back my take back. No, it is going to be P of 16 minus P of 15. And you could do that same P of 16 minus P of 14 over 16 minus 14, and whatever you get there as your how many you should expect in the following year. But I was going to say that was going to be my initial take back, but my take back to my take back is you can also explain that the model predicts this many people in 1996 minus this many people in 1995. And that would be how many additional people the city would expect in 1995 in that additional year. Anyways, back to our present. Back to the present day. Okay, back to this instantaneous rate of change estimate. So P of 2, we know that P of 0 is 180 still, but so P of 2 is 4.5 times 2 squared minus 15 times 2 plus 180, and then our P of 0 gets the minus 180 taken care of. So it's effectively this. 4 times 4.5 is 18. 15 times 2 is 30. So 18 minus 30 over 2, negative 12 over 2, so negative 6. So I don't have opposite signs there. Oh. We got a winner, folks. For part A, they want 1 to 5, not 0 to 5. So we're just gonna edit that real quick. So 117.5 minus, okay, plugging in 1, we get 1 times 4.5 minus 15. 4.5 minus 15 is negative 10.5 plus 180. That is, okay, I'm gonna do the math on the calculator and get back real quick. Okay, wow. This is 217.5. I'm so sorry, folks, about that oversight. Knew something was off there, you know? So 217.5. So regardless of this other mistake, oh sheesh, that's embarrassing, folks. That is super embarrassing, but I'm human and I'm here with you. When you find a mistake, just got to go back and correct it. That's what it comes down to. Okay, 217.5 is our P of 5. Our P of 1 is going to be negative 10.5 plus 180. So 169.5. Okay, that is 48, negative or positive 48 over 4. Positive 12.0. Median home price increased an average of $12,000 per year. Okay, now that's fixed. Okay, this is still true. Interpret your answer. The median home price was dropping at an estimated rate of $6,000 per year on January 1st. What? 2011. Boom. What does this indicate about home prices? C, home prices go up and down. Over time. Especially up and down over time. And I'll say semicolon. A short-term trend may not be indicative of the long-term trend. Boom. Okay, folks. That's homework. That's homework 2, technically. And the one other point I wanted to make is what is listed on the very front of your homeworks, which is that if you are using this, if you are looking at this, you do have to give a disclosure. Where is this? Statement acknowledging any collaborators at the top of your first page of your submission. So other people have put me on their disclosures before, and I don't want you to get in any trouble if you do use this video, and don't write that down. So put that disclosure down, and for the ones going forward. So I hope this helped. I apologize for some of the algebraic and just oversight mistakes towards the end there. I hope you loved it. I hope you share it with some of your classmates, and we will see you in the next one. Homework 3. Let's do it.